right? So this would be a material that has no planes of symmetry. If we go into the lab and basically any way we rotate or orient the material, we would get different Young's modulus properties. I'll talk a little bit more about material properties in a second. But if we went to the lab and cut multiple pieces at different orientations out of a rock or a plate of steel or whatever, and then started measuring it, in every single different orientation we measured, we'd get different properties. Right? And luckily, there's not many materials like that, right, that have no planes of symmetry. So if we consider a plane of symmetry, so for example, if you have a coordinate system and the plane x1, x2 is a plane of symmetry, then we might write down a rotation matrix. And it's actually not a proper rotation matrix. It's a more, I guess, a reflection matrix. But we can use it in the same way we use a rotation matrix to transform the stress. So in other words, if we said sigma prime is equal to R sigma R transpose, then what we would get, sigma 1, 1, sigma 1, 2, minus sigma 3, 1, sigma 2, 2, minus sigma 2, 3. And similarly, for the strain tensor, so we could transform the strain tensor the same way. And if we did that, I'm not going to write the whole thing out, but we'll get that epsilon 3, 1 prime is equal to minus epsilon 3, 1, and epsilon 2, 3 prime is equal to minus epsilon 2, 3. All right, so what I'm going to do is I'm going to write out the generalized elasticity equation just for the 1, 1 component of stress of the transposed stress, or not the transposed, the rotated or reflected stress. So that's just the 1, 1 component of stress, okay? Now, I'm going to substitute in these relations that we know, like that the 3, 1 prime is equal to negative 3, 1, 2, 3 prime is equal to negative 2, 3. And the other ones are the same, right? So now I get a minus sign. Minus okay. Now, if the x1, x2 plane is a plane of symmetry, then this rotated stress, which again is not rotated, let's call it reflected stress. This reflected stress, if it's a plane of symmetry, that reflected stress should be the same as the unrotated stress, or unreflected stress. Right? So, and this is the last long equation, sorry, but we're going to write down the unrotated stress. Okay, so like I said, if the plane is a plane of symmetry, then sigma prime 1, 1 minus sigma 1, 1 should equal 0, right? That's another way of saying that they're equal to each other, right? Sigma prime 1, 1 is equal to sigma 1, 1. Another way to say that, sigma prime 1, 1 minus sigma 1, 1 is equal to 0. Right? So let's then subtract these two equations from one another, right? Or the second from the first, and see what happens, right? We know on the left-hand side, if it's a plane of symmetry, that should be equal to 0. So this equation minus that equation should equal 0 on the left-hand side. Let's see what happens on the right. I'm just going to write down the result. All right. So that's what you get on the right-hand side when you subtract those two equations one another. And so the only way, this equation should read 0 equals 0, right? So the only way that can happen for any arbitrary strain measure is if the coefficients C1131 and C1123 are equal to 0. So C1123 equals C1131 equals to 0. All right. Now, that's just that was just we just wrote down one value, one component of the stress tensor. There's 9 more, right? So, or 8 more. Now, I'm not going to write all those, do it all over again, but basically using similar arguments. We can show that if there's a single plane of symmetry, then all those components are also 0. So then the full C matrix, again in Voigt notation, so this is called a monoclinic material. And it has 13 independent constants. Did I miswrite something?
Second term of the first one.
Second term.
Second column right now.
Yeah.
I think it's 1, 1, 2, 2. Then the other one is 2, 1, 1, 3.
Second